Next we have Shuichi Ihara and Luigi from Data Direct Networks. The title of the talk is OSD-Btrfs, a Novel Lustre OSD-Based Btrfs. Shuichi Ihara, Senior Manager, Advanced Solution Laboratory at DEN. He joined DEN in 2010, made new benchmark center and DEN also in 2010. He ran more than 100 Lustre benchmarks for customers for the past 4 years. His responsibilities benchmarking, performance optimization, and managing Lustre development. Managing Lustre development team at DEN. He was working at Sun Microsystems for 10 years and deployed in several large HPC systems. Luigi is a senior Lustre developer, Advanced Solution Laboratory at DEN. He joined DEN in 2012 and has been a Lustre and Linux kernel developer for more than 6 years. Has contributed a ton of code to the Lustre ext4 and other open source communities. Before DEN, he was working at Jiangnan Institute of Computing Technology and developed several storage software, including distributed file system based on Lustre. All right. Shuichi, Lee, you got it. Let's give him a hand.
I'm Shuichi from DEN, and my colleague Shuichi Ihara, and we will talking a little bit about OSD-Btrfs. It's a Novel Lustre OSD based on Btrfs. So the first question we would ask is, why do we want to use Btrfs for Lustre? As we know, Lustre we use ldiskfs, or more recently ZFS, as a packaging file system. And ldiskfs is a patched version of ext4, and we know ext4 is widely used, and it fits well to performance, and it has good reliability. However, these techniques are old, and the limitations are increasingly apparent. And ext4 is missing some important feature, its reliability, and its offline FSCK is low. While by contrast, ZFS is an extremely feature-rich file system. However, it seems that we need to optimize further to improve the performance of ZFS OSD. And unfortunately, there are some licensing and potential legal issues which have prevented a broader distribution. So, because of this reason, we have to look for some alternates, and we believe that Btrfs is a good option because Btrfs shares many features and goals with ZFS, and it is becoming sufficiently stable for production usage. And we can get the Btrfs from a lot of major mainframe Linux distributions. We want to use Btrfs for Lustre, mainly because Btrfs has a lot of good features. Some features can improve OSD internally. For example, the integrated multiple device support. We can use grade 0 to generate less OSDs on each OSS and get better performance from single OSD. And the more we can use maybe grade 1 or other grade level to improve the reliability of the OSD. And another core feature is that Btrfs can allocate the anodes dynamically, and we don't need to worry about formatting the NDT using wrong options like ldiskfs. And the Btrfs can calculate the checksums of both data and metadata. So that could improve the OSD reliability. And what's more, Btrfs can do online file system check, and it clears that Btrfs has very fast offline file system churn. It is important because drivers are becoming very big, but not very faster. So this will lead to increasing SDK time. There are also some other features which will enable us to implement some features for Lustre itself. For example, the features of snapshots, subvolumes, compression, send and receive feature, duplication, left link. We can look through this list and make some Lustre features based on this feature. Of course, there are some issues we need to think about. We need to maybe fix in the future. For example, BTRFs doesn't have the user group or project quota. Quota is very important for Lustre because typically Lustre file systems are shared by lots of users and organizations. So actually, BTRFs has quota, but it is falling quota. It might not be sufficient for some use cases, and we need to maybe add a user group code in the future. Another problem is that the offline FSDK tool is still under development. Well, maybe BTRFs doesn't need offline FSDK tool, offline FSDK because it is almost self-scaling. Sometimes users just want to run FSDK, no matter whether it is really necessary or not. Another problem is that we need to make sure whether the performance of BTRFs is enough for the OSD or BTRFs. We need to check the concurrency, we need to check the scalability, and of course, we need to check whether the reliability of BTRFs is enough. We need time to prove BTRFs is stable enough. Okay, we have been working on BTRFs SD for almost 4 months, and our primary goal is to implement a BTRFs SD prototype. So we want to make sure what we need to do to implement BTRFs SD. We need to ensure BTRFs is scalable enough. We need to learn what we need to do to improve the performance of BTRFs SD, and we need to learn what features we need to implement to support existing and future Lustre features. So in the process of implementing BTRFs OSD, we refer to existing OSD types, and we find that there are a lot of common codes between different OSDs. So we suggest that we can maybe put some functions in a shared library to reduce the code redundancy in the future. We made our patches based on CentOS 7 kernel, and we believe CentOS 7 is going to be used as the main distribution in the next few years, and we export some BTRFs, almost all of the BTRFs patches from upstream Linux kernel to CentOS 7 kernel, and we didn't get any performance improvement. So we believe that the performance of BTRFs on CentOS 7 is good enough. And we change the build system of Lustre. We make sure all the BTRFs in the code are replaced by ldiskfs to avoid conflicts. And ldiskfs module is built separately, and we can generate 2 additional RPMs. As soon as we install these RPMs, we can use BTRFs as the OSD type of Lustre. And also we add utility support for BTRFs OSD, and we can use the great feature of BTRFs SD in the OSD. Another important thing about the implementation of OSD-Btrfs is object index. Internal to the OSD, the object index table is used to map the quantity to the inode, and we add a new item type Btrfs to map that ID to inode. However, this will introduce less metadata overhead than other implementations, such as directory-based implementation. However, we have to update Btrfs CK to support the new item type, and that's a thing we need to commit to the Btrfs. Another thing is that we add the transaction callback to the Btrfs. Last one is transaction callback to the resource D, the internal resource, after a transaction is committed. We have to pass Btrfs a little bit to this report, and we have to pass it more to add operations of objects, such as object creation, deletion, read, and write. Also, we calculate the item numbers of each kind of transactions we need for different operation types. We might need to calculate it more carefully to make sure every number is correct. Another important thing is zero copy I/O. So last zero copy I/O is very important for performance because we need to bypass the memory copy to achieve good streaming I/O. In this process, pages are locked, and we need to pass Btrfs to make sure these pages will not be released during this process. And there is a problem with this is free annual number. Btrfs doesn't have free annual number because the annuals are allocated dynamically. But Lustre needs that number. It needs to calculate the free annual number when it's a pre-trained object. So we have to apply a patch to estimate the free annual number according to the used blocks and make a data space. Well, I think this implementation might have some problem, but we need to check it in the future. Okay. Generally, we have implemented a prototype of Btrfs OSD, and we will go working on it in the future. And I believe we can make a reusable Btrfs OSD in maybe 1 or 2 years. And I have the confidence because we have an active community, and when we ask for help, we get the help very soon from the community. And I'd like to thank Intel people for the help we have got in this process. And I think I have to.
Okay, so we implemented. We started this project last December, then implemented the first prototype last month. So there is really a limited benchmarking time. So primarily focusing on the throughput benchmarking at this moment. So this is a configuration of test configuration. So we have a VDN SFA7700. This is a small hardware storage box. We have a 80 and Ihara as well. We still keep the hardware configuration under the Btrfs. So we create the 8.6 volume, and we have 2 OSS and 1 MDS. So each OSS has 4 OSD. Then maximum we have a 32 wire, then connected to 18 1. We selected the Red Hat the enterprise server, the 7.1, the new version. because they have a new BtrFS code from the upstream, so we use this base operating system. Right now, all the BtrFS patch or Lustre BtrFS patch are based on the master branch, so we also use a master branch as well. So how to make a OSD using the btrfs? The procedure to install the Lustre, 99% is the same. So we need to just install Lustre RPM package, but except the new BtrFS RPM package, because we have a new backend file system. So you need to install two additional RPM package. At this moment, so we don't support the btrfs for the MDT. So ldiskfs still required for the MDT. So we just format the MDT ldiskfs and mount it. Format OSD using the btrfs. Syntax is the same, except the backend file system type. We have a new backend file system type, the btrfs. So you just set the btrfs instead of ldiskfs or ZFS. So other options are completely the same. So we had additional the option to MKFS Lustre to use the btrfs software level capability. So as you know, the btrfs has a software level capability. So we can make a big OSD using the btrfs software layer. We had additional new option to MKFS option. So you can set the BtrFS level here. Then point the number of the OSD to making the big OSD. Then finally, so you just mount the OSD. Before the Lustre benchmarking, so we just run hardware benchmarking to make sure that what is the hardware the performance and what is the hardware capability. So we run the XD to the low device without the Lustre. This is a sequential read on the right using the direct I/O. So there's no the caching on the OSS side. The left side, that is a light performance. Then left side is right side is the read performance. Blue bar, the 1 megabyte block size. Then red bar is the 4 megabyte block size. As you see, when number of the LUN increased, so finally we go to the maximum 10.5 gigabyte per second. So that is for read on the right. So that is a maximum the peak performance of the hardware. That is the hero number of the hardware. Okay, so this is a IOR benchmarking from the client. So this is a standard IOR, the 5-bar process, from the service client. We just run the light testing first, and after that, so all file cache, remove flush all the file cache from the OSS and the client. After that, the real testing. So we also tested the number of the Lustre RPC size because improve the real performance. So left side, so that is a 1 megabyte and 4 megabyte Lustre RPC size result. So you can see the dark blue line, that is how we have the peak performance because they are using the XDD. Then you can also see the light blue line, so that is the performance IOR number for the light performance from the client. So light performance is pretty good. So we achieved more than 95 or 100% the hardware capability. However, so you can see the red line, so that is the read performance using the 1 megabyte Lustre RPC. So peak performance is okay, but so when number of the IOR process increase, so the performance is significantly go down. So we tried the larger RPC, 4 megabyte RPC. So that is the light, the green line. So we see the significant performance improvement for read. Then finally, so we tried the additional extra patch to support a more larger RPC. So we run the 8 megabyte RPC. So the read performance is even better than compared to the 4 megabyte RPC. And finally, we got so 91, 95% of the peak performance for write, and 17 or 75% of the hardware peak performance for read. So the initial number is quite nice. So this is the same IOR benchmarking, but just compared to the ldiskfs. So we also run the same benchmarking using the ldiskfs on the same hardware. So left side is the same, so write performance. So blue line, that is ldiskfs, and the red line at the OSD-Btrfs. So as I said, so write performance is always better than the ldiskfs. So one interesting, so when number of the processes is increased, so we see the performance go down a little bit on the ldiskfs. However, you can see the Btrfs, so we can keep the peak performance even the number of steps increase. And so read performance. So read performance is almost close. It's very similar behavior on the ldiskfs and Btrfs. So that we got the 90 or 95% of the hardware peak performance. Then we dropped a little bit the performance after the number of the threads increased. But the finally average, we got the 17 or 75% of the hardware capability for read. So the write performance is very good, and the read performance is almost same compared to the ldiskfs. So this is another benchmarking result. As I said, software Btrfs has a software-led capability, but we didn't. So we cannot remove the hardware-led at this point. So we created the software-led or software-led on top of the hardware 6 volume. In this case, 2 RAID 6 volume was struck by Btrfs to RAID 0. So that will help to reduce the number of the OSD from the 8 to 4. So left side is the same, the write performance. The right side is the read performance. Blue bar, that is the baseline number. We got without the Btrfs software-led capability. But once we create the RAID volume using the Btrfs software-led, so that is a red line, a red bar. So we see the performance drop after that. So we confirm, so because of the Btrfs, the chunk size is very small on the fixed size. So that is the 16 kilobyte. So we change the chunk size, we change the Btrfs code to support a more larger chunk size up to the 8 megabyte. Then after that, so we run the IOR again. So that is the light green line. So after the increase the chunk size, so we significantly better performance in the light. Then very close to baseline number without the software rate. But the read performance still a little bit, we increased a little bit from the default chunk size, but if we compare to the baseline number, so we see still a little bit the performance drops. So we might think there's a performance optimization area here. So the conclusion, so we designed the new OSD, the backend file system, based on the EPFS. Then so we just implement the simple prototype existing the Lustre OSD framework. So most of the code is the new code. So we didn't change any the framework. So it's everything is based on the existing OSD framework. And again, so there's very limited benchmarking time, but so the initial benchmark result so very attractive and encouraging. So we very surprised. However, so this is one of the IO workload. So we need to more the fundamental benchmarking. So even so right now we are only focusing on the OSD, but we need more fundamental IO operation, the file creation, operation, and the rewriting, because this is the copy write file system. We need to compare to ldiskfs. So that is we want to investigate in the future. Thank you.
I wonder if you looked into stability of Btrfs using all of that and even outside of your exercises. Have you had any problems?
Yes. So we didn't much, testing time. Didn't have much testing time. So during the test, so we didn't see any the Btrfs itself the problem. So most of the code problem is our new OSD area. And also I agree, so this is a very new so local file system. However, the Linux distribution included for example the SLES12, so that is a UTF-S is a default file system. So maybe we see some problem in the future, but Linux vendor fix it as soon as possible. So maybe we see a lot of the problem, but fix it as soon as possible. Hopefully, so stability testing.
Okay.
So some of the performance issues that we have to do developing ldiskfs have to do with locking and commits, operations that you've identified here, reading files, things like that. Have you done any comparison between Btrfs and ldiskfs in this area, and which do you believe would be most suitable for optimization around those sorts of documentations? Some of the things that we tried to do, for instance, was could we identify inodes or bitmaps, map those select devices that were SSDs or other higher performance devices. And so the way that ldiskfs allocates these structures makes it very difficult to vector those types of data to different media types. And so other file systems have mechanisms to do this, right? And, so that would be an area of interest to something that's sort of a broad question.
Right. Well, so if we compare the between the BTFS and ldiskfs, so we see that a little bit the performance goes down on ldiskfs. However, you see we got more than 7.5 gigabytes per sec. So only the 8 near isosceles. So that means 19.5 or 95 megabytes per sec per wire. Right. So still we see that a little bit down, but still acceptable.
But so the issue though is when the I/O rates go to 0 because you're backed up on some mid operation, and so then your request queues expand and gate counts and everything get crazy, and the response times have to respond. start to result in phone calls. And, so that's kind of the issue. A lot of times that gets back to metadata issues on the OSTs themselves.
Yeah.
Anyone else? Shuichi, thank you very much. I think this is really important work. One more.